Hello learners, and welcome to today's lesson of geometric patterns. Let's start off our lesson with a did you know? So, did you know that there is mathematics in art? Geometric patterns are found in so many different artistic representations. These include paintings, decorative materials, and even in traditional attire. Look at the example below of this beautiful geometric pattern. Let's see what we are going to learn in this lesson. So by the end of this lesson, you should be able to investigate and extend geometric patterns, write rules in words to describe relationships between diagrams, represent geometric patterns in tables, and work with patterns that have a constant difference, a constant ratio, and neither a constant difference nor a constant ratio. Looking at the concept map for our lesson today, our main focus is the geometric patterns, where we are going to look at the representation of geometric patterns in tables and algebraically. Then we are going to be solving problems, where we are going to look at solving for complex problems involving geometric patterns. Let's see what pre-knowledge we must have for this lesson. So you must be able to investigate patterns within numbers, describe the numeric pattern in words, find the general rule of numeric patterns, and find the value of any given term in a numeric pattern. Let's start off with our first question. So here, given the following numeric pattern, write down the next two terms. Now remember, for us to find the next two terms, we need to see what the relationship is. So from 0 to 5, we can say that they added 5. So we add 5 from the first term to the second term. Remember, this is the first term, the second term, the third term, and the fourth term. Then from 5 to 12, we are adding a 7. Then from 12 to 21, we are adding a 9. So as we can see that with the numbers that we are adding, or the difference that we are getting here, it is not the same, meaning it's not constant, but we can see that each time we are adding 2 more than we previously added to the previous number or to the previous term. So what would be the next 2 terms? So from a 21, we know that we are going to add not 9, but we are going to add 11. So 2 more than the difference that was added initially. So from 21, when we add a 11, we are going to get a 32. So the next term here would be a 32. And of course, we are required to get the next one as well, where we are going to add 13 to this term to get the next term as well. So 32 plus 13, that is going to give us a 45. And those would be the next 2 terms. Now describe the numeric pattern in your own words. Now, as we have stated here, that the difference that is being added is 2 more than the last difference. So we can write that down here to say that each difference added is 2 more than each difference added is 2 more than the last difference. So each difference added to the terms, the previous term, maybe we can add that as well. Each difference added to the previous term is 2 more than the last difference added. So that would be our numeric pattern in words. Let's go over to the next question and see if we can answer that. So now we are given another numeric pattern, and that is 2, 5, 8, and 11. The first thing we need to do is to write down the first 3 terms. So for us to write down the first 3 terms, we need to know what is happening with this pattern. So from 2 to 5, we can see that we are adding 3. From 5 to 8, again, we are adding 3. From 8 to 11, again, we are adding 3. So this means that we have a difference, a constant difference of a 3. So what would the next 3 terms be? Well, when we add 3 to 11, we will get a 14. And when we add 3 to 14, we will get a 17. And when we add 3 to 17, that will give us a 20. And those are the next 3 terms. So then we need to describe this numeric pattern in our own words. So we can see that we add 3 to the previous term. As we've already discussed, we are just adding 3 to the previous term to get that next term. Now we need to describe the numeric pattern using an algebraic representation. Now if we remember, that is us now finding that rule. And we know that to find that rule, we need to take the constant difference, which is the 3. We're going to multiply it with our term number, and we are going to add or subtract any constant. So for us to be able to do that, we are going to use the first term. Now the first term would be 3 multiplied by 1. What do we add or subtract to get to the first term, which is 2? We can see that here we are going to subtract 1 because 3 multiplied by 1 is going to be 3. And when we subtract 2, that is going to give us 3 multiplied by 1 is 3, and when we subtract 1, that is going to give us a 2. What about any term here in the sequence? We can use the 4th term. So we are going to say here 3 multiplied by 4, and we are going to add or subtract something to get 11. So 3 multiplied by 4 is 12, but when we subtract 1, we definitely get an 11. So this term here is going to be described algebraically, or this pattern here is going to be described algebraically by saying it's the constant difference multiplied by the term number, and we are going to subtract a 1. Lastly, we are going to find the 15th term. So we are going to use our rule to find that 15th term, because remember, our n represents our term number, meaning we can now use our formula to find any term in the sequence. So that is going to be our 3 multiplied by our 15, and we are going to subtract 1. The answer there for the 15th term, do you think you have what it is? Well, if you have there a 44, then you are absolutely correct, because 3 multiplied by 15 is 45, and we subtract 1, which is going to give us that 44. Then we have a constant ratio, which is represented by an R, and that is a value obtained by dividing the second term by the first term and the third term by the second term. That is, R is equals to T2 divided by T1, which is equals to T3 divided by T2. So for example, in the sequence 2, 8, 32, the constant ratio is 4 and is obtained by calculating 8 divided by 2, which is equals to 4, or 32 divided by 8, which is equals to 4. Then we have term number, and that is the position of the diagram in a geometric pattern. Now, for example, in this pattern that has been shown here by figures, the third figure would be then the third term over there. Then we have the rule, which is more of a formula. Tn is equals to 2 is a rule for a pattern. It is a formula or an equation, not an expression. For example, in the sequence 2, 4, 6, the rule is to multiply the term number by 2. And then with consecutive terms, terms that follow each other numerically. For example, in the sequence 1, 4, 7, we can say there that 1 and 4 are consecutive terms. Let's quickly go to an ad break, and then we'll see you just now.